Good evening to all. Myself, Arun Kumar. I'm going to talk about steady state error. So, in control system, the steady state error is one of the factor which will affect the total control of the systems. So, in order to find the steady state error, one of the method which is used for finding the errors is called static error constants. So, in this video, we are going to see how the static error constants has been followed by using the characteristic equations. So initially the error has been generated based on the input and output signals. So here the values are assigned by using the above things. First one is R of S is the input signal and C of S will be the output signal and H of S is the feedback signal. Initially the input signal is applied in the summer signal. The summer will be generated as the error signal and the error is given to the output signal. The output is forwarded to the summer as -1 and the feedback will be collected as HFS and the same CFS and HFS will be offered to the minus summer signal and totally we will get the output in the error signal EFS. So the formulation of error signal can be calculated by using the above equations. EFS equal to RFS is input signal minus CFS into HFS. So based on the input and output signals, the error has been generated. Finally, the calculation of error, total error value can be calculated by EFS equal to RFS divided by 1 plus GFS into HFS. The errors are normally generated by using a time signal. So based on the time domain signal, the error can be calculated in the transition equation by Laplace inverse of R of S by S plus 1 plus G of S into H of S. And next one is static error constants. All those error constants are identified by using the following principles. Initially, the error constants are identified by type 1 and type 2 systems. So type 0 system also there. Type 0 system means it doesn't have any value. So it will be comes under positional error constants. So for the following equation can be used for the positional error constants, limit s tends to 0, g of s and h of s. And next one is type 1 system. The type 1 system is used for velocity signal or ramp signal. The velocity and ramp signal can be denoted by the characteristics equation by limit s tends to 0, s into g of s and h of s because it's an order 1. And next is type 2 system. So type 2 system will be applicable only for parabolic and acceleration signals. So the formula of the parabolic and acceleration signal will be limit s tends to 0, s square, 0 of s and h of s because it's a type 2 system, so that the order will be s power 2. Like that, all the system will be arranged based on the types. And next one is the characteristic equation has been framed in the number of systems, especially for positional velocity and acceleration systems are denotified by the number of system is if it is positional error means then the type 1 system will be infinitive and the next also infinitive because it's a type 0 system, so it will be available only in the 0 system. Like that, all the values will be arranged and calculated by using the same properties. And if it is all the values acceleration and parabolic will be implemented only the signals. The signals are generated based on the below principles. First one is a unit step signal is because it's a 0, order is 0, so it will be generated in a 0 itself. Next one is ramp signal. Ramp signal is type 1 order, so that it will be generated in 1 by kV is it is in first order. And last one is unit parabolic. It will be comes under type 2 system, so that it will be generated only in type 2. Remaining will be in zeros and infinity. And next one is the properties will be implemented in the like formulas like that C0 and C1 C2. In previous we will discuss about how the parameters will be assigned in the types and number of the systems. The same will be calculated and the same will be implemented for following problems also, especially for positional and velocity error constants. These formulas will be implemented. And next one is problems. So in the problem we are going to see how the uh, properties will be implemented in these equations. The equation is g of s equal to 10 into s plus 2 s square into s plus 1. Here we are going to calculate the positional and velocity and acceleration error constants. Initially we are going to calculate the error constant by using the uh, following properties. First one is static error constant. Error constant will be calculated by based on the type systems, type 0 and type 1 and type 2 systems. Initially we are going to calculate the error constant like positional error constant. It is a type 0 system, so we are going to apply the same formula for this positional error constant. After applying the following formula for this positional error constant, we will get the final answer. So 0, so don't doesn't have any value. Next one is acceleration. So acceleration means already we have discussed about the formula s into g of s. So s will be implemented, and after that we will substitute the initial s value, so that we are getting the final output of the corresponding equation. And next one is acceleration error constant. The same, it is a type 2 system, so that it will come s square into g of s into h of s. So we will get the final answer as 20, because s square and s square is cancelled, and remaining will be get as a final answer. And steady static error, the error can be calculated by using the following formula, because already they are in question, they are given about the formula and equation also. Based on the equation only, we have to substitute all the values. After that we will get the answer. So initially they are given about r of s value. Based on the r of s, we have to substitute the concern property equation. So after cancelling with each other, we will get the final answer like this, 1 by 60. So this will be our static error constant of the concern equation. Thank you.